Hello, everyone. My name is Raul Jordan, and I am a staff software engineer here at Offchain Labs working on the Arbitrum Bold implementation. Today, we're going to be doing a walkthrough of the whole Bold smart contract suite and understanding how it all fits together, talking about terms that we understand are new and can be kind of confusing. And we'll be talking about what Bold is really at a high level, what it actually accomplishes. We'll be talking about the different entry points, going deeper into the actual code and the logic, and we'll wrap up by essentially just talking about some of the other resources and tools that folks have available as part of looking at Bold. Cool. So without further ado, let's get started. Arbitrum Bold stands for Bounded Liquidity Delay Protocol. And essentially, this is a new dispute system for Arbitrum chains. The idea is when you bridge over from Ethereum into Arbitrum, Arbitrum reads from the Ethereum state, so there is no trust involved. But when you go back from Arbitrum to Ethereum, there is a process via which a claim to withdraw can be disputed. And this system is really crucial and critical for the security of the chain to exist. We want to claim that as long as there are honest parties that are monitoring the state of withdrawals from Arbitrum, then Arbitrum Bridge is secure. What makes Arbitrum Bold special is that it's very robust against delay attacks. So a very common type of dispute problem in naive protocols is that somebody could initiate a dispute over a withdrawal claim, and they can kind of burn their stake and keep initiating more disputes, delaying the confirmations, and basically just delaying the withdrawals of everyone that is trying to bridge back. What makes Bold also special is that essentially we have a guaranteed upper bound on the confirmation of challenges. What Bold does really is that it makes sure that withdrawals from layer 2 to layer 1 are safe. And safe means that nobody can essentially claim an invalid withdrawal and be able to execute it correctly as long as somebody is able to make a dispute. How this works is that every hour, essentially, claims about execution of the Arbitrum inbox are posted to Ethereum. We call these claims assertions. It's going to be a very important word in today's video. The key thing is that these can be challenged, right? So somebody is saying that, hey, after I executed these Arbitrum transactions, essentially, I obtained this layer 2 block hash, right? So, because the Arbitrum state transition function is deterministic, every single block that you consume and process will produce, a new block. Every transaction that you consume and execute will essentially mutate the state of the chain. You're making essentially a claim about what the execution of some transactions are. So what is the Arbitrum inbox? So the Arbitrum inbox essentially is a system where anyone can post layer 2 data to a contract on Ethereum. And today we have a sequencer that actually rolls up a bunch of L2 transactions from users, compresses them, and posts that data to Ethereum. However, users can also post their own messages, kind of circumventing the sequencer if, for example, the sequencer becomes malicious or if the sequencer goes down. Users can still get their Arbitrum transactions included on-chain, right? Arbitrum essentially derives its state and its chain from this data that is posted to Ethereum. However, the data that is posted is basically just raw bytes, right? So it's just a raw user transaction data. There's no information about how this actually changes the Arbitrum state. There's no information about how it touches accounts, for instance. And there are no claims of execution, which is the main thing that we're trying to get at here, right? So if you look at the data that's posted to the inbox contracts, you get the call data or the blobs. It's just a bunch of raw bytes. You don't have anything doesn't really tell you anything about, say Arbitrum accounts, who has this balance, who has that. Somebody has to then execute that. So that's where the second mechanism that Arbitrum rollup has, which is something called the Assertion chain. So the idea is that essentially every 15 minutes or so, assertions can be posted to Ethereum. And what this is, it's essentially claims about executing the inbox. So if I say, hey, after consuming 100 inbox messages, my layer 2 block hash is ABC, for example, right? And at the time that I posted the assertion, more messages could have arrived in the inbox. So I can immediately say, okay, the next assertion that follows this one should consume at least 105 inbox messages. So then the next person comes in, or the same person that is posting this, the same entity, consumes 105 messages and gets block hash at layer 2 0xDEF. So these entities that are posting assertions, essentially, they are executing these messages, this transaction data using a layer 2 node, and deriving basically a block hash from that result. The assertion chain, it's basically a smart contract that contains a linked list data structure, right? So you post an assertion, it claims its parent, it also claims what the next assertion should consume in terms of the inbox, and each assertion contains information about this execution, right? That's what makes it special. So it's not like a software separate. This is on chain. This is on Ethereum, and you can actually see this as part of rollupcore.sol, which we're going to be covering today as well. The key thing is that assertions can be confirmed, and they actually have a 7-day dispute window. So this is a sliding window, right? Like you can imagine everything inside the pink. This window is moving forward to the right, and every assertion that's kind of below the window is confirmed, right? So essentially, we have the 7-day sliding window of confirmations, right? A very important property is that forks can occur in this assertion chain. So what this means is that somebody makes a claim, and at say inbox position 105, and then somebody says, "Hey, wait a second! I executed the same number of inbox messages, but I received this block hash. So I disagree with your result, right?" And this person can be evil or they can be honest. We don't know yet, right? That's what bold comes in. What this means is somebody disagreed with the result of execution. And that's really important because it's going to be able to help us figure out how we can actually resolve this dispute and get to the bottom of the dispute. In this example, I'm tagging the evil and the honest parties clearly, but from Ethereum's perspective, Ethereum doesn't know who is honest or who is evil, right? It just sees data being posted. There has to be a mechanism via which a winner can be declared from this, because Ethereum has no knowledge of the actual layer 2 state, right? It doesn't know who is telling the truth. So what happens if there's a dispute? So what occurs if there's a dispute essentially is the parties that are involved in this dispute need to essentially provide proofs of execution. So the way they do so is they provide basically from inbox position 100 to 105, they provide a proof of all the block hashes in between. And the goal of the dispute protocol is to narrow down the disagreement, right? So essentially what they're going to do is they're going to do this binary search where they make a claim of 5 blocks, for example. They're going to split that in two. They're going to split that in two, and essentially find a single block where they disagree. So the key thing is we want to narrow down actually to a very single block, and that's not even the end of the dispute protocol. Our goal after that is to figure out exactly where in the execution of the block the parties disagreed. And we'll talk about that next. Right? So here we have an Arbitrum block. Let's call it block number 100. And after you run it through the Arbitrum node, through the state transition function, you obtain the resulting block, which is Arbitrum block 101. Right? So you start from some pre-state block, you execute some transactions that are within, and you arrive at some final result. And this is native execution. This happens in Go because Arbitrum Nitro is currently written in Go. But it basically is done on a node that you're running on your own computer, right? Our goal is to figure out where the parties disagreed. Somewhere along the way in this execution, something happened that went wrong, and something occurred that just led to problems. So we need to figure out where that exact point was. So how do we do that? The way that we do that is that Arbitrum actually has an emulator of the state transition function, and this emulator uses WebAssembly opcodes. So what it does is that it converts the Go logic that's above in the pink area into essentially this emulator code that we can then run step by step, right? So we can actually execute step by step, and at each step we can actually create a unique hash of the emulator state. What this means is that at some point, maybe like let's say step 1 million, we're going to figure out that that's the point where the evil party and the honest party received a different result, right? So each step has its intermediate hash. We proceed, and essentially we make some progress after that, right? However, we have a pretty big problem in that essentially, the execution of a block through this emulator can have a lot of steps, right? So we could have 2 to the 42 or more instructions, and this is a pretty unbelievable number. It's a very, very large number. If you're trying to represent every single hash, that's an unbelievable amount of data. No computer has, the single amount of capacity to store that data. So if we're trying to actually provide proofs of computation, we have a lot of hashes, too much data. How can we actually do this? The idea is that, instead of collecting a bunch of hashes for every single step, we instead step through the emulator in large sizes. So we step in large step sizes. So for example, here we say, hey, we're going to collect 16,384 hashes, but we're going to do that in step size of size 2 to the 26, right? So if you do this, you'll be able to claim the whole execution of the block, but with a lot smaller data granularity, and it's a lot better, larger data granularity, and you get actually easier to represent this data. Right? What we do after we collect all our hashes is we create basically a Merkle commitment out of them, and we essentially receive a single Merkle root that represents this whole computation. Right? This is called the history commitment. And what this history commitment does for us is it allows us to do, very powerful things, such as, for example, you can Merkle prove a single step. So I can say, hey, I can prove that, basically this step is what I claim, and this is the step that the other person claims, and here's where we disagree, and here's this overarching commitment to my data. Right? One really powerful thing about using history commitment, so why do we want to do this and not just claim a single hash? It's a really critical property for Bold that all honest parties agree on one history, right? So imagine that I make a Merkle commitment to every step from 0 to 2 to the 40. Honest parties will agree with everything, and evil parties will disagree. So the Merkle root of this tree is the same for all honest parties, right? All honest parties have the same history commitment. They all agree, and they don't need to necessarily, fight 1v1 against the evil adversaries that are trying to claim different things in the dispute, right? Like I mentioned, 2 to the 40 steps is a lot. It's a very large number, and especially if we need to do a lot of hashing, we need to do a lot of Merkleization and things like that. We can't be doing this, right? So we need to play the game at smaller levels of granularity, right? The analogy that I like to give is essentially a meter stick. So imagine that essentially we have 2 meter sticks, and they essentially look the same, right? So we have these 2 1-meter sticks. They look very similar, but they actually have a small difference in their actual in the actual material that they're made out of. So we need to figure out where we disagree. So the way we're going to do it is we're going to be basically figuring out where we disagree at the centimeter level. Once we figure out what centimeter we disagree at, then we grab a magnifying glass, we look deeper and figure out, okay, where do we disagree at the millimeter level? Then we go to the micrometer level, and so on and so forth until you get low enough that you can figure out exactly where the point of dispute was. So that's kind of what Bold does. So when we see the terminology, challenge levels, multi-step, we're referring to this level of granularity. Why? Because there are so many steps in the execution of an Arbitrum block that we need to essentially narrow down at different levels of granularity. And that's a very important topic that we'll be covering in today's walkthrough. All right, so enough talking. Let's go deeper into the code. Alrighty. So where do we begin? The key thing is we're going to begin with the actual assertion chain. So where assertions are actually being posted. The main place to look is inside of the rollup folder of the contracts repo inside of a file called rollup user logic. So anyone who is a user of the rollup can essentially post an assertion by becoming a validator. And we're going to be looking at this deeper. Okay. So the key function we want to look at here is this one called new stake on new assertion. What this does is if you're basically posting an assertion for the very first time, you need to attach a stake. We also call it a bond. that essentially is placed on your assertions. Next time you post assertions, you don't need to post a bond every single time. Instead, your bond just is moved to whatever latest assertion that you posted. So if it's the very first time that you have posted an assertion, you want to be calling new stake on new assertion. What this does is that it essentially, it stakes your tokens based on some withdrawal address. We can then actually, it actually relies on the stake function for the new assertion. What this function is going to do is it's going to perform some validation. So it's going to make sure that you are staked, that you are an active staker in the rollup chain. What it's going to do is that the parent assertion that you're claiming exists. So recall that essentially the assertion chain is a chain. Each assertion claims a parent, and an assertion can have many different children. There are certain conditions here about kind of who can create an assertion or whatnot, right? So if everything succeeds, then we go into this create new assertion function. Right? Recall that assertions are claims about execution of an inbox, of the Arbitrum inbox, right? The thing that is executing this stuff is known as a machine. The machine is also the emulator that we discussed earlier in this video. And essentially, a machine can have different states once it executes inbox messages. For instance, executing a bunch of inbox messages might lead to an error, and that's why you might get the machine status errored claim, or it might lead to finished. Finished is basically that the machine completed successfully, it produced a new block, executing the inbox messages was correct. So we want to make sure that the thing that you're posting makes sense, right? Another thing that matters is that if you recall, an assertion chain is basically a claim of executing the inbox. Something very important is that when you post an assertion, say for inbox 100, when you posted that assertion, in that time, there could have been a lot more messages arriving to the inbox. So basically, at the time I posted this assertion, 5 new messages were received in the inbox. So the next assertion must be for at least 105 messages. So on and so forth. We have this consumption, basically check of the inbox. So a lot of the logic that you're going to see here, a lot of the arithmetic here, checking around, the integrity of assertions is explained here in the comments. But what we care about is essentially that, you're consuming the right number of messages in the inbox. You want to check that the machine actually finished, and that it actually, did not error. It consumed all the messages correctly. Cool. If everything succeeds and all these different checks succeed, then we're actually going to create the assertion containing the fields that we want, and we're going to actually emit the data, right? If there is a fork in the assertion chain, so for instance, let's go down here. If we have a fork in the assertion chain, then a dispute must be initiated, right? So where does a dispute actually begin? And yeah, let's look deeper into this. So the dispute mechanism for Bold is actually handled in a contract called the challenge manager. And this is inside of challenge v2, edge challenge manager.sol. And here you'll have a variety of methods, right? So essentially, we have this function called create layer 0 edge. So an edge essentially is, some commitment to some start state and an end state. Recall that in our graphic here, for instance, we have Arbitrum block 100, Arbitrum block 101. So an edge is essentially a commitment from 100 to 101. It contains a history commitment and the information that we need to validate to make sure that the computation makes sense. So to actually dispute an assertion, you need to call a function called create layer 0 edge. This is the entry point for a dispute. And we're going to be looking deeper into this function. Cool. So what we're going to be checking is if the challenge manager is permissioned, then we're going to check some permissions. For Arbitrum 1, the challenge manager will not be permissioned. It will launch permissionless out of the gate if the DAO approves to do so. The next thing that we're going to check is we see some information about challenge levels. So if you recall, imagine that we have a dispute over a 1 meter stick. We start with disputing over the centimeter level, then we go to the millimeter level, then we go to the micrometer level. So we do something similar here in Bold. So we start at disagreeing about Arbitrum blocks, and then deep down we go into disagreements about actual steps of WASM execution. So The block level, E-type is the type of edge. So a block type edge is basically the highest challenge level inside of Bold. If your edge is a block type level, then we have some specific logic here, right? So what we do is that we validate, the previous assertion in your claim, the latest assertion in your claim. We make sure that everything matches up. And if everything works and makes sense, then we're going to be actually creating the edge. And at the end of the function, we essentially, you also need to put some stake or a bond on this layer 0 edge you're creating. We're going to be transferring that essentially to the contract or to some excess state receiver if it exists. Let's look deeper into the function that creates a layer 0 edge. Right? So what this is going to do is it's going to validate some proofs, right? So when you create an edge, you need to create a proof that the previous history is a prefix, of course, of the suffix history that you're producing. There are certain specific checks at different challenge levels that we need to enforce. And also there are some common checks that all edges need to enforce, right? The important thing is, at the end of the day, what's going to happen is I create an edge, another party creates a rival edge, and after we are rivaled, then we need to narrow down our disagreement further. We're going to get to that in a second. So let's look a little bit deeper into some of these checks, right? So if the claim that you're making is over an assertion, so if the block challenge level is essentially the highest challenge level, the biggest granularity, we're going to check that the assertion that you're claiming, it exists, it makes sense, that it's not pending, that it is not already confirmed or rejected. We're also going to be checking some information about the machine execution that you are providing. And we're going to be basically validating some information about the proofs, right? There are also some common checks that all edges have to do. So, claims, history commitments are actually powers of 2. If, for instance, maybe they're, like the actual number of steps of execution is not a power of 2, then we pad that information. And what this function does is it's going to verify the proofs that you're providing. So we're basically providing Merkle proofs that, hey, my history commitment is correct. It actually represents this history, and it represents this start hash and this ending hash, and we're going to be validating that is true. After you create the edge, we add it to a mapping in Solidity, and we're essentially done here. And essentially, so we created our layer 0 edge. So that is awesome. So we're done here. Next, the other party will create their own layer 0 edge as part of the function. So what's going to happen is they will also call this method, create layer 0 edge. After two edges are rivaled, so if you have edges that are rivals, essentially, they have the same starting point but a different ending point, such as, for example, in this assertion chain fork. These two assertions are rivals, right? They have the same ending, but they have the same parent. So you're going to do something very similar here in this challenge manager. Essentially, edges can have a very similar representation. So once you are rivaled, the next step that you need to do is you need to narrow down your claim. So narrowing down your claim means bisecting your history commitment, okay? So you're going to say, hey, I'm giving you a proof for steps 0 to 2 to the 40. Then I'm going to give you a proof for 0 to 2 to the 20. And you're going to be basically breaking down in half each time. And that way, playing this game, as long as every party is playing the game, we will eventually narrow down to a single step of disagreement. So the next function that we want to be looking at here is this function that's called bisect edge. So we're going to be looking at this right here. So bisect edge basically takes in an edge ID, which is this layer 0 edge that we just made just now. You need to provide it a proof that, like, hey, I'm bisecting to a valid history. That's a prefix of the history that I gave you earlier. And what this is going to do is it's going to create two children. It's going to create a lower child and an upper child, right? So if I bisect an edge that goes from 0 to 2 to the 40, I'm going to have two children, one from 0 to 2 to the 20, one from 2 to the 20 to 2 to the 40. So you're producing two children each time you bisect, right? The idea is that you can only bisect if you are rivaled. So for instance, if I'm not rivaled, if I create a layer 0 edge and it's been 20 minutes, and it's been half an hour, 1 day, I don't need to do anything else. But if I'm rivaled, the honest party needs to then bisect. The goal is the party that is ahead is basically accumulating time, and after a certain period of time, that entity will be able to get their edge confirmed on chain, right? So, as an honest party, as soon as we have a rival, we want to be able to bisect. We want to be able to bisect on time, right? Now let's look deeper into the bisect edge function. Okay. So what this is going to do is it's going to go into this library here. It doesn't do much inside the actual contract, but in the actual library implementation, it does quite a lot of things. So of course, there are a few invariants that we have when we're trying to bisect an edge. So first of all, we want to make sure that the edge is pending so that it's not confirmed. We want to make sure that the edge has a rival, so you cannot really bisect if you have a rival, right? That's part of the rules of the game. You don't want to make sure you cannot bisect twice. And then we do a few checks. So we basically verify the proofs that you're providing. We verify the prefix proofs. We check then at the end of that, that okay, let's try to create children, and let's store them in the system. So something else that happens in the game is after a while, you're going to reach a point where you cannot bisect anymore. So imagine that we reached an edge of length 1. So it goes from history from block, maybe let's say 100 to 101. Then we can no longer bisect. So what's the next step after that? What's our next step of this agreement? The next step of this agreement is just like in the meter stick example. We have to go down from the centimeter level to the millimeter level. So we have to go here from one challenge level to another challenge level. And we have to call the function create layer 0 edge again. This time, instead of the edge claiming an assertion, it's claiming that step 1, that length 1 edge that we just discussed. So it's saying that like, hey, I disagreed at the centimeter level, we're going to go down to the millimeter level, and here is where kind of we started at the higher level. So we're going to be entering the else branch, essentially, of this function of create layer 0 edge, right? So there are quite a few different things that layer 0 edges do. So here we have some specific checks. If an edge is a block challenge edge, like for example, like a centimeter challenge versus a millimeter challenge. Otherwise, we have some other specific checks that occur to make sure that we have integrity in the creation of the edge. And you can see a lot of our unit tests also to understand how some of these functions are called and setting up, for example, this multi-level bold challenges, because we understand that it's quite a lot to cover. And we'll be talking about some of the unit tests soon. So eventually, you're going to reach a challenge level that's the lowest level possible, and you're going to bisect until you reach a length that is length 1. At that point, the only thing left to do is to basically prove to Ethereum that, hey, this edge is correct. And we do that through something called the one-step proof. So we have a function called confirm edge by one-step proof. What it's going to do is essentially, it's going to check that this edge is the lowest level of granularity, and it's going to make sure that, hey, this one is correct, this one is evil, and you're going to be able to win essentially that specific edge and confirm it right away on Ethereum. So what's next after we confirm by one-step proof? The next thing that we need to do is, okay, at that point, there's nothing really left to do in terms of bisections, but we're still not done with the challenge. So the next step that we need to do is essentially we need to confirm our branches up the tree. So imagine we created basically a tree all the way from the top, all the way to the bottom at some one-step proven edge. We need to confirm that tree basically by time. So we have a function that's called confirm edge by time. Essentially, every time you make a move and you are unrivaled, you are accumulating time. Time in the protocol is denominated in terms of block numbers. So essentially, if I make a bisection and the other evil party has not rivaled my bisection, those two children are accumulating time unrivaled, right? The idea is that once your whole path of edges, all the way from the bottom all the way to the top, accumulates enough time greater than a challenge period. So a challenge period is 7 days, give or take. You can essentially confirm that edge. Once that edge is confirmed, then you can confirm once the whole branch is confirmed, you can then confirm the assertion that originally started the challenge. I'm going to be looking into confirm edge by time. Okay, great. So what this function is going to do is it's going to make sure that that the edge that you're creating is basically a layer 0. It's a root edge, basically a root edge of the challenge. And it's going to be also inheriting the time that its claimed assertion was unrivaled. So we want to also make sure that happens. If we meet the threshold that is required, then we're going to actually confirm the edge, right? So we're going to make sure that the edge exists, do some basic integrity checks. We're going to check that the total time unrivaled for the root edge is greater than or equal to a confirmation threshold. And if so, then we're going to be confirming that edge. So how do edges, how does this timer propagate all the way to the top, right? Because we confirmed the one-step proof edge at the very bottom, but now we need to confirm this thing at the very top. How do we actually propagate that? So the way that we do that is edges actually inherit a timer from their children. And essentially, if you think about it, if the bottommost edge is gaining a lot of timer because the evil party cannot challenge a one-step proof, eventually the bottommost part of the tree will have a huge amount of time unrivaled, and that's going to propagate up to the top. So we call that timer inheritance. It's a very important part of how Bold works also. The function that is responsible for that is actually how do you actually do the timer inheritance kind of thing. We're going to be talking about that next. Cool. So essentially the way it works is that we cache this timer on chain, and you can actually update this timer cache by calling this function. It essentially refreshes the time inherited from the children. And to basically propagate up the tree, you have to call this update timer cache by children for every any honest basically branch along the tree all the way to the top. And if each edge updates its inherited timer from its children, at the very end of that process, the topmost edge will have enough time to confirm. So we call this a timer cache. If you see timer cache, it essentially refers to this cache value on chain. We only update it here if it changed, right? So if you have a timer that is greater than what existed before, then we should update what exists on chain. Otherwise, we don't want to make any unnecessary state modifications. Once a challenge is basically complete, so that means that the initial layer 0 edge that we created to dispute an assertion is confirmed by time. The next step is to actually confirm the assertion that it corresponded to. So if you go back to rollup core, there's a function that's called confirm assertion. So confirm assertion, if there is no challenge, you can confirm an assertion if 7 days have passed, right? Also, the previous assertion must be the latest confirmed. There are a few other invariants here that I won't go into detail, but you can read them here. They're explained in every single comment. However, the condition in line 115 here, if the assertion has a second child, that means that there is a dispute. Then we need to make sure that there is a winning edge that claims that assertion from the challenge manager contract. And if so, then that means that we can confirm the assertion by challenge winner. So what's going to happen is, we are basically finished here. At that point, essentially, validators will be able to get honest validators could be able to get their bonds refunded. So validators can get their layer 0 stakes refunded back to their addresses. And also validators that are creating assertions on chain can also unstake their bond and take it home and stop posting assertions. So I would recommend looking at these entry points, thinking that the key things to keep in mind is, one, to recap, you want to make an assertion, you're going to call this function stake on new assertion. You want to dispute an assertion, you're going to create a layer 0 edge for a claimed assertion hash. After that, the evil party must also create a rival edge. After that, both parties need to bisect their edges and narrow down their disagreement. And each time, whoever makes the move, gets it first and is unrivaled, is basically getting advantage because their timer is increasing. At the very end of the system, once the timer cache is big enough, then you can confirm basically your whole challenge, honest challenge branches by time, which is very effective. Cool. There are quite a lot of other helper functions and things that occur as part of an invariant that occur as part of the function, but I would recommend looking at those key components of the Edge Challenge Manager and understanding kind of how they fit together now that we covered them. And we really hope that this was very helpful. I would also recommend what would be helpful is to start looking into some of the tests. So we have quite a lot of tests for challenge managers. So you can have information about here. We have example tests that, for example, check all the different invariants. We have tests that, let's see if we can find something here. Yeah, so we have examples here of like creating a few edges, 2 layer 0 edges, and bisecting until they discover that they have a fork. That's very important. We have examples of confirming edges in bisections and doing all that kind of stuff. So there's quite a lot here. We have tests for bisecting, tests for all kinds of things. We also have rollup t.sol, which actually tests the challenge protocol. So here, for example, here you can see how a challenge is created. Basically, there's a fork, and somebody creates a layer 0 edge. And you can see more detailed tests also in the challenge manager t.sol, so you can understand better how actually disputes are resolved and what actually occurs in the setup. Excellent. So thank you so much for joining us. We appreciate your time and hope we can this gives a little bit more clarity to kind of what this all means and how it works. But of course, it's a big project. It's quite complex. Let us know if you have any questions, and we'll be there to help you. Thank you all.